This video is about understanding the connection between the equation of a wave and what that looks like on a graph. The maths is exactly the same as that needed for oscillations in simple harmonic motion in year 13. We're going to start by plotting x equals 3 cos pi t. So that's the displacement x of a point on the wave at time t. We are keeping our calculations in radians throughout, and we're going to plot x for 0 to 2 seconds. Pause the video and use the formula to fill in the table. Okay, here are our values. So it's a cos graph going through these points. Now remember that this graph shows the movement of a point on the wave, and we can see that the amplitude of the wave is 3 meters. Comparing this graph to the equation, we can see that the amplitude is here. What about the time period? Well, we can see that the time period of the wave is 2 seconds, but how does this fit into the formula? Well, it turns out that the general equation for a wave is as follows. Displacement of a point on the wave is the amplitude times cos of omega t, and omega is the angular frequency. By analogy with circular motion, we know that omega equals 2 pi over t, or omega equals 2 pi f. So we can also write the equation for the wave as x equals a cos 2 pi over t times time, or x equals a cos 2 pi f times time. This is because we're measuring in radians, and so 2 pi over the time period times t, that's the fraction of the wave that's gone by. Let's see how that works for the graph we drew before. We've got displacement equals the amplitude times cos of 2 pi over the time period, which is 2 seconds, times t, which simplifies to the equation we started with. So now we don't need to calculate a table of values before we can plot a wave. Suppose we were told that the equation of a wave was x equals 7 cos 5 pi t. We would know that the amplitude is 7 meters. We also know that 2 pi over t times t equals the thing inside the trig function. So that's 5 pi t for this wave. And so we get this and this, and t equals 2 over 5, that's 0.4 seconds. And our wave looks like this. Pause the video now and have a go at exercise 1. One final complication to add is that the equation doesn't have to be a cos graph. What do we mean by that? Well, if you think about our point on the wave moving according to this equation, we can see that at t equals 0, so that's when we start the stopwatch, the point on the wave is at amplitude position. But we could have started the stopwatch when it was at equilibrium, or at negative amplitude, or anywhere else. So what would that have done to the equation? Well, if you think about starting the stopwatch here, the particle is going this way, so the graph would look like this. And that's a minus sign graph instead of a cos graph. So the equation is minus 3 sine pi t. But everything we said before is the same. This is still the amplitude, and the expression inside the trig function is still 2 pi over the time period times t. What if we started the stopwatch here? Then we get this. Which is a minus cos graph. So the equation is minus 3 cos pi t. And finally, if we started the stopwatch here, we'd get this, which is a sine graph. So the equation is 3 sine pi t. But in each case, the amplitude and the time period can be identified in the same way. Starting anywhere else will add a constant term to the equation, but you won't meet that within the A-level syllabus. Now try exercise 2.